Welcome to the fifth session of Business Mathematics. In today's session, we'll be looking at approximate integration. The session objectives should be able to understand how to integrate a function using the approximating techniques, the importance of approximating techniques for integration, the two rules under the approximate integration, i.e., the trapezium rule and the Simpson's rule, right? Sometimes we can find the integral of a function, or we should know that under integration, the area of interest is that we are finding the area under a curve, right? The area of interest is that we are finding the area under a curve. So we can either use the trapezium rule, the Simpson's rule to also find these integrals of the functions we are given or we have. Okay. Approximate integration. Sometimes it is difficult to integrate a function using the techniques we've learned under integration, right? Or the basic rules under that. For example, it will take a considerable effort to find the integral of the integral of upper limit 2, lower limit 0, an exponential function to the power x squared, right? So integral upper limit 2, lower limit 0, e to the power x squared dx. Below is the curve e to the power x squared dx, right? Between the interval 0 lower limit, 2 upper limit, right? The area under the curve between this interval is equivalent to the integral upper limit 2, lower limit 0, e to the power x squared dx. Therefore, it is too difficult to integrate such a function. So we could take a shortcut by rather finding the area under a curve, right? So this is the curve that we're talking about, how it looks on the diagram or the graph, right? How do we deal with these problems? To deal with this problem, the approach is that the shape under the curve might not be a nice one, right? With an already established formula for finding the area, like say triangle, a rectangle, sphere, right? Any shape, right? In an attempt to find that area, some scholars proposed dividing the area under the curve into sub areas with some triangle, some rectangle, it could be some trapezium, some parabolas, okay, to help us estimate the area under the curve. So there we come to the types of approximate integration, or the two rules that we have under that. First one is the trapezium or the trapezoid rule. Second one is the Simpson's rule. We are going to look at the first one, which is the trapezium rule, and we'll deal with that, and then we'll come back to the second one, the Simpson's rule, right? The trapezium rule is also going to help us to estimate the area under a curve when it becomes too difficult to find the area under the curve given, or the curve we have, right? Simpson's rule is just an old approach, right, that helps in the estimation of the area under a curve. The general idea about this approximate integration is that you should be able to know the coefficients of each of these rules, right? This trapezium rule is born from the idea of finding the area of a trapezium, right, which are saying that it is 1 over 2 the horizontal distance plus the two vertical distances here, right? Okay. So given a curve as shown below, we could divide the area under that curve into a number of trapezoids, right? Or into a number of equal sized trapezoids. And we find the area of each trapezoid. We sum them together to get an approximate value of the area under the curve, right? We are unable to estimate the area under the curve, so we just divide the curve into equal size, right, trapezoids, i.e. we divide them into trapeziums or trapezoids of the same sizes so that we can find the area of each trapezoid. We add them together, then we get the approximate value of the area under the curve, right? So this is the trapezium that we have here, and then we know the area of a trapezium, right? Okay, note that the emphasis on approximate, there will inevitably be some leftover areas that won't be covered by the trapezoids. Okay, so that is why it is approximate integration. We don't use the normal equal to sign. We are going to use the curvy looking equal to sign, right? Because it's approximate. Why? Because when the trapeziums or the curve is divided into equal sized trapeziums, there will be some leftovers in that curve, right? You're not going to be able to cover all the curves with the trapezoids that we have, right? Okay, so we don't use the normal equal to sign. We use the curvy looking equal to sign, right? Remember, I was talking about the coefficient of each of these rules, right? And the trapezium rule, you need 2 points. The trapezium rule, you need 2 points to be able to estimate the area under the curve. And the Simpson's rule, you need 3 points. Here we are fitting, or we are dividing the area under the curve into trapezoids or trapeziums, and we need 2 points. Okay. On our next slide here, it's a curve here, right? Say a diagram that shows how the trapezium rule formula came about. Okay, so this is it. You see, we have our curve here, and then the curve has been divided into equal sized trapeziums or trapezoids, right? See, it starts from A, right, to B, or f of A plus h, f of A plus 2h, f of A plus 3h, f of A plus 4h, all the way to f of B, right? So the curve has been divided into equal size what trapeziums. The equal interval, that's the horizontal distance, right, from A to B over here. We say we are going to find that horizontal distance here by using the upper limit and the lower limit of the function given. So to find the horizontal distance, it is equal to b minus a all over m. B is the upper limit of the function. A is the lower limit of the function. We divide this by n. N here is the number of trapeziums or the number of trapezoids, right? And A and B are the endpoint, A here and then B here. To find the area under a curve using the trapezium rule, this is the procedure that we go through to be able to estimate the area under a curve. This is how the formula was brought about. You go through this series of steps to be able to arrive at the final answer, right? So it is 1 over 2 h. So 1 over 2 here, we need 2 points, right? That's why it's 1 over 2. And that trapezium rule, you multiply it by the horizontal distance, and then you pick the first, that's the i.e. the starting point. You have f of a. F of a, we keep on adding horizontal distance to it, so it will be f to bracket a plus the horizontal distance, same here, We do this until we get to the final point, which is what? FOB, right? Let's look at an example that will help us to understand this critically. So an example is that we have to find the area under the curve. See the integral with upper limit 1, lower limit 0, 1 over 1 plus x squared dx. The actual answer for this function over here is 0.785. However, this integral is not that easy to find. We could approximate the area under the curve using the trapezoidal or the trapezium rule. The function is 1 over x squared plus 1. And then what does it mean? So let me explain this function here. You can be given something like this, or you have a function like this. There could be a follow-up question, say this function with n being equal to 5 or 6. Okay, and use the trapezium rule to estimate this function here. The lower limit of 0 here means that you are starting with 0. That is your starting point. And then the ending point is 1. This 0 is a starting point. 1 here is the ending point, right? So this is your B in the horizontal distance formula. This is your B. This is your A. And then the N is the number of trapeziums that will be given to you in the question, right? So this is how it is being shown on the diagram, right? How you are going to estimate this function or this question here, right? Right. Let's look at how we're going to solve this. We can either solve questions under trapezium rule using the formula here, right? Or we can use the table as well. There's a table, a way of going about is using a table with just 3 columns. Okay, so for the purpose of this class, I will go through the series, or I'll explain to you how you deal with that using the table, right? Okay, so we just need 3 columns, 1, 2, 3, like I said earlier. So finding the area under the curve using 10 trapezoids of equal base height. Okay, so to find your h, it is b minus a all over n. Now, if you're given a number of trapeziums, right? So upper limit here, we have 1, lower limit 0. So our h is 1 minus 0 all over the number of trapeziums, which is 10, right? It is going to give us 0.1, right? So this is how you find your h, which is the width of each of these trapezoids that we have, right, in the curve, and it is denoted by h. So this represents the width of each trapezoid. So it is upper limit minus lower limit all over number of trapeziums. You have 0.1 here. This is how you deal with it using the table approach. So we have 3 columns here. The first column is the variable you have in the function, right? Is it given in terms of x, given in terms of y, given in terms of q? So looking at the question here, the function was given in terms of x, right? It was given in terms of x here. So the first column, you just write your x. On the second column, what you write in the second column is the function itself. The function itself is 1 over 1 plus x squared. That's what we write here. Okay. On the last column, on the final column, what we do is that we are going to multiply what you have here, right? What you have here by the coefficient under the trapezium rule, right? So what are the coefficients of the trapezium rule? The coefficient of the trapezium rule is saying that to get that coefficient, it is 1, right? The coefficient of the trapezium rule is 1, 2, 2, 2, 2, 1, right? It is 1, 2, 2, 2, 2, 1. So these are the coefficients. It says that it is 1, 2, 2, 2, 2, 2, right? 2, 1, right? So these are the coefficients of the trapezium rule. It simply means that you're going to multiply the first number you have, right, on the second column by 1. You multiply all the middle numbers you have by 1. Multiply the last number too by 1. So basically, the first number is going to be multiplied by 1. You multiply the last number or the final term with 1. All the terms in the middle are going to be multiplied by 2. Right? So this is the coefficient we are going to use under the trapezium rule. So it's 1, 2, 2, 2, 2, 1. Right? So that's it. This ki here is representing the coefficient of the trapezium rule, the coefficient under the trapezoidal rule. So you're going to multiply those coefficients by 1 over 1 plus x squared. That is the values that you get here. Right. Remember the lower limit is 0, upper limit is 1. It means that the starting point of this function is starting at 0. It is going to end with 1. So you begin with 0 in the first column, and the last value you have in the column should be 1 for the first column. So you can see here, the first column we began with 0. We begin with 0, right? To get this next point, what you do is that you add the width or the age value you had to 0. So you keep on adding 0.1 until you get to 1, which is the upper limit or the ending point. So 0 plus 0.1 gives you 0.1. 0.1 plus 0.1 gives you 0.2, and so on. You are going to get the final term here or the ending point 1. Right? I hope you all get this clearly. The next thing, or what you have on the next column, has to do with the function itself. What you do is that just substitute the 0 or the values you have here in place of x. So 0 in place of x gives you 1. 0.1 in place of x here gives you 0.99, and so on and so forth. You have these values over here on the second column. On the final and last column, what you do is that you multiply the values here in the second column by the coefficients under the trapezium rule 1, 2, 2, 2, 2, 1. The first value here, 1, is going to be multiplied by 1. The last value here, which is 1, is also going to be multiplied by 1. The terms in the middle, or the values in the middle, sorry, are also going to be multiplied by 2, 2, 2, 2, 2, 2, 2 each. Right? So 1 times 1 gives us 1. 2 by this 0.99 gives us 1.98. This by 2, this by 2, this by 2, this by 2. And we have these values here. And you can see that the final value here, 0.1, is also multiplied by 1 and gives us what? 0.5. Okay. On the next thing, or on the next step after doing this, what you do is that you just add the values in the last column. So 1.98 plus 1.92 plus 1.82 plus 1.72 all the way to the final one. You sum all of them, and that gives you a total sum of 15.68. Right? That is the summation of what the values you have in the last column, right? And the final step is that you're going to find the area under the curve, and we need 2 points under trapezium rule. So to find the area under that curve, you are saying that it is h over 2 times the sum, right? So h over 2 times the sum. What did you get as our width of the trapezoids? It is 0.1, what you have here. So h is 0.1 divided by the 2 points that you need, then you multiply it by the sum of the last column. So 0.1 over 2 times 15.68 gives you 0.784, right? But we don't use the equal to sign, we use the curvy looking equal to sign because we are dealing with approximate integration, right? It's not approximate. Sorry, it's not equal to, but it's approximately equal to 0.784. So here we use the curvy looking equal to sign. So that's how we deal with the trapezium rule here under approximate integration. Well, let's continue on then. Look at the other rules and the approximate integration. So you can try this, right, using a trapezoidal rule, okay, with say the number of trapeziums being equal to 8. You can try this as well and then we'll be good to go. Looking at the other one where we have Simpson's rule, here we are fitting parabolas under a curve. So we use what is called a parabola. And then with the Simpson's rule, we need 3 points. Remember, trapezium is 2 points. Simpson, here we are fitting parabolas under a curve. So we need 3 points. That's why it is h over 3. Right, the distance between the vertical lines, this is the h, or the width divided by 3 because we need 3 points. So we can also approximate the area under a curve using a parabola instead of the trapezium. This is called the Simpson's rule. The sum of all the areas, right? The sum of the areas of all parabolas under the Simpson's rule is giving us, right? So this one, or this rule, also has a coefficient for the rule, right? So the area is h over 3, f into brackets a plus 4f into brackets a plus h. Remember, you keep on adding the width or the h to it until we get to the ending point, which is the upper limit, right? So you see it is 1, coefficient here is 1, 4, 2, 4, 2, 4, 2, 4, 2, 1 here, right? So the caveat here, or I would say that the coefficient under Simpson's rule is 14242 right? You multiply the first number that you have by 1, the last value 2 by 1. The terms or the numbers in the middle are multiplied by 424242 each, right? So when you get to the final value, it is multiplied by 1. Now, there is a condition here that must be satisfied under the Simpson's rule. It is saying that the number of parabolas that are fitting under the curve must be even. So n should be equal to an even number before you can use this Simpson's rule, right? Let's take a practical example under the Simpson's rule. Use the Simpson's rule to approximate the total revenue received from the production of 80 units of a product if the values of the marginal revenue function, that is the R over the Q, are as follows. Here we have the quantity from 0 to 70, our marginal revenue to be what? 10 all the way to 7 here. So we've been given our quantities, the marginal revenue values. We can find the h, which is our width or the distance between the vertical lines we have. So to find your h, it is your upper limit minus lower limit over the number of parabolas. Okay, so we have the quantities here, the marginal revenue values here, right? But how do you find our h? Remember, the ranges of the product start from 0, right, to 80 units. So we were given here already that we're going to find the total revenue from the production of 80 units. So it means that the upper limit is 80, the lower limit is 0, right? Upper limit here, lower limit here. So 80 minus 0 over n. That's the number of parabolas. When you count this, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, 9 is a prime number. But there was a condition under Simpson's rule which was saying that the number of parabolas we are fitting under the curve must be even, right? So it means that the number of parabolas is what? The number of parabolas is 8, right? Instead of 9. So we can't write 9 here. Remember the caveat that we had earlier. It must be even. It is 9 because you have, sorry. Yeah, okay. It's a 9 because there are 9 points here, right? One, that is 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 points here, but the intervals are 8, right? So remember, if you have the number of parabolas to be 8, then when you have the points, it should be 9. So if the number of parabolas is 8, then the number of intervals or the number of parabolas is 8, then the number of points you have here should be 9. So when you have 8, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it means the number of parabolas was 8, right? And then that will give you 10. Now the next thing is to multiply the coefficient of the Simpson's rule by the marginal revenues you have here. Remember, you're looking for total revenue. To get your total revenue, it is the marginal revenue times quantity, right? Okay, so what you do is that these are the marginal revenue functions here, or the values here. The first coefficient is 1 by 10, 4 by 9, 2 by 8.5, 4 by 8, 2 by 8.5, 4 by 7.5, 2 by 7, 4 by 6.5, 1 by 7. You can see it is 1, 4, 2, 4, 2, 4, 2, 1. First value of the starting point by 1, or the terms in the middle by 4, 2, 4, 2, 4, 2 each, 4, the final one by 1. Okay. Then if you multiply everything here, you should get 10, 36, 17, 32 to 7, right? The next step is to add all these values here from 10 to 7, and that should give you the total sum of 189, right? That is not the final answer. And then you find the area. It is h over 3 because you need 3 points. You multiply it by the total sum of 189. So the h, which is the width, we had 10. That is 10 over 3 times 189. And that should give you an approximate value of 630. So approximately equal to 630. It means that the total revenue from the production of the 80 units of a product, right, is 630 maybe Ghana cedis or dollars, right? Okay, let's move on to the final part where we have to deal with certain things under economics, i.e., producer and consumer surplus, right? This is just the diagram that shows the demand curve and then the supply curve. Remember, producer surplus has to do with the producer surplus here has to do with supply, right? That's the area of interest for producers. For consumer surplus, the area of interest is the demand function, right? So here you have P1, we have P0 here, we have price 2, we have the quantity here. Now, where the P0 and then the Q0 intersect, there is a equilibrium point. The quantity demanded is equal to quantity supplied, right? So this is the point here, P, which is our equilibrium point. Now, you have the demand curve here, which is downward sloping, right? We have the supply curve also here. Now, the point over here is our equilibrium. This shaded region here, right, between P1, P0, here, right? This triangle over here represents your consumer surplus. The other triangle here where you have P0, P2 here is also your producer surplus, right? So if you have something like this where you have the P1 being the demand function, P0 quantity at price at 0, or the initial price, sorry, P1 here is the demand function, P0 here is the initial price, P2 here is the supply function, Q0 here is your initial quantity, right? So for any quantity below Q0, there is a consumer surplus of P1 to P0. So any quantity below Q0 here, there is a consumer surplus of what? P1, P0. P1, the demand function, P0, the initial price, right? So that's DQ. For any quantity, for any DQ quantity below Q0, there is a producer surplus, right? That is P0 minus what? P2. So the initial price minus the supply function. Okay. The total consumer and producer surplus are given us. To find that is the integral, that is consumer surplus, the integral with upper limit, the quantity at 0 or Q0, lower limit of 0. And then you have the demand function minus the initial price. To find out of the producer surplus, it is the same integral with upper limit Q0, lower limit 0. Then you have the initial price minus the supply function DQ. Then you can estimate the producer surplus as well, right? An example to show how you go about these two formulas over here to find the consumer surplus and the producer surplus, right? So the demand function for a product is P, which is equal to 100 minus 0.05 Q, where P is the price per unit for quantity Q. The supply function has been given here also. Determine the consumer and producer surplus under the market equilibrium, right? First of all, we need Q0, right? We need Q0 to be able to estimate the consumer surplus and the producer surplus. What do? We find the equilibrium points or our equilibrium. Equate these two functions and then you will get the equilibrium points. That is Q0, you're going to get P0 as well, right? So we have Q0 to be 600, P0 to be what? 70 here, right? We can find the consumer surplus integral of upper limit Q0, lower limit 0, P1 demand function minus P0 initial price, right? So we have integral 600, upper limit, lower limit 0. Then the demand function is 100 minus 0.05 Q minus 70, right? Then remember 100 minus 70 will give us 30 over here, right? Give us 30 minus 0.05 Q. The next thing is to integrate. So when you integrate the function that you have, that is 30 minus 0.05 Q, you're going to get 30 Q minus 0.025 Q squared, right? The next thing is to substitute the values of the upper limit and the lower limit. Remember, it is upper limit minus lower limit after getting this integral function here. Upper limit is 600, so that one comes first. 30 minus Q. Q is 600 now. So 30 by 600 minus 0.025 into bracket 600 squared, right? Minus, then you do that of 0, which is the lower limit, to 30 by 0 minus 0.025 by 0 squared. That will give you 0. So the summation of this should give you 9,000. So that is the consumer surplus. Same for the producer surplus. It is integral Q0, upper limit, lower limit 0, P0 minus P2, the initial price minus the supply function. So upper limit here 600, lower limit 0. The initial price was given as 70. We had 70. So 70 minus brackets of the supply function 10 plus 0.1 kill VQ, right? After multiplying through by the negative sign and then doing our subtraction, if there's any, you should get 60 minus 0.1 kill. Then you integrate this function, right, to get 60 kill minus 0.05 kill squared here, right? Okay, the next thing is that after integrating, just put the values of the upper limit and the lower. Put the upper first into the same function you have here, right? Minus, then you pick the lower 0, put it in Q here, then you subtract the two values. So you see this function here is the integral function. So 60 by the upper limit 600, that's in place of Q, minus 0.05 times bracket of 600 squared, minus, you do the same thing for lower limit 0, 60 by 0 minus 0.05 by 0 should give you 0. So the total here minus 0 should give you 18,000 as the producer surplus. I hope you all get this idea about consumer surplus and producer surplus. Thank you so much for watching. I really appreciate your time and support. If you found this video helpful, don't forget to like, comment, and subscribe. I'm excited to meet you again in the next session where we'll dive even deeper. See you soon. Goodbye.